Think of a Java class as an architectural blueprint. It defines the exact structure of a system, what variables it holds, and what methods it can perform, but it has no physical mass. It is purely abstract potential. On the other side of the equation is the computer's raw memory, known as the heap. The heap is an unstructured expanse of hardware potential waiting to be organized. The core engineering problem is figuring out how to take that abstract blueprint and manifest it physically in the heap as a secure, usable data structure, an actual object. This bridge between concept and physical memory is called a constructor. It is a specialized initialization mechanism built directly into Java to handle this exact transformation. To function, this mechanism must follow strict syntax rules. The first is that the constructor must have the exact same name as the class it belongs to. If the class is user, the constructor is user, matching capitalization perfectly.
While it might look and act like a standard method on the surface, the compiler enforces completely different constraints upon it. The second strict rule is that constructors inherently lack a return type. You cannot even declare them as void. The logic here is absolute. A constructor does not return a string, an integer, or a Boolean, because its singular, exclusive purpose is to return the newly minted object instance itself. Furthermore, you do not call this mechanism manually. It triggers automatically the exact microsecond you use the new keyword to create an object. Constructors function as the mandatory starting point for every object, establishing the internal rules that raw memory must follow to become a usable instance. Suppose you write a Java class and compile it without including any explicit instructions for how to build the object. Instead of throwing an error, the Java compiler silently intervenes. It injects a hidden mechanism into your code to ensure the initialization process doesn't fail. This injected mechanism is the default constructor. You can identify it by its empty parentheses, meaning it accepts exactly 0 parameters. The compiler does this to guarantee memory safety. The default constructor carves out a rigidly defined boundary in the heap for the new object. Within that object space, any uninitialized variables could cause system faults if left completely empty. So the default constructor populates them with safe placeholder states. Any numerical variables, like integers, are instantly snapped to 0. Object references, which are variables designed to point to other objects, are locked to a state of null. And Boolean variables, which handle true or false logic, default to false. This ensures every single object instantiated in Java has a deterministic, predictable starting point. It acts as an invisible baseline safeguard against system crashes, even if that starting point contains no usable data. The limitation of relying entirely on a default constructor is that it yields a blank placeholder. This forces the programmer to create an empty object and manually write subsequent lines of code to populate each variable with real data. The architectural solution to this inefficiency is the parameterized constructor. This is a constructor explicitly designed to accept external data inputs at the exact moment of creation.
The parameters defined inside the constructor's parentheses act as direct injection points into the object's allocated memory space. By routing data immediately into the object, this mechanism completely bypasses and overwrites the default 0, null, or false states. This allows the system to assign custom, highly specific values to an object in a single operation. Parameterized constructors enforce immediate data integrity. The object arrives in memory fully configured, accurate, and ready to execute its intended function immediately. Real-world software requires flexibility. A single class blueprint often needs multiple, distinct pathways for creation, depending on what data the system has available at execution time. We manage this complexity through constructor overloading. This is the practice of placing multiple constructors inside the exact same class. Remember the absolute syntax rule. Every single one of these multiple constructors must share the identical class name. To coexist without causing a conflict, each constructor must possess an entirely unique configuration in its parameter list. When the system requests a new object, it passes along a specific set of arguments. The Java compiler evaluates the data types of those incoming arguments against the entire vertical stack of available constructors. It scans the options until it locks on to this singular constructor signature that perfectly matches the incoming data types. This routing mechanism relies on compile-time polymorphism.
Compile-time polymorphism is the process where the compiler determines the exact execution path of a method or constructor before the program ever runs, guaranteeing strict type safety. There is a final restriction to note here. While constructors can be overloaded horizontally within a class, they can never be overwritten vertically by a subclass in a larger inheritance hierarchy. Overloading allows a single class to resolve multiple initialization paths at compile time, ensuring the correct constructor is matched to the available data with deterministic precision. The creation of an object is a highly regulated transformation, turning an abstract class blueprint into a functional physical memory structure. That process operates under twin constraints: identical class naming and the strict absence of a return type. This matrix shows three primary initialization strategies. The default constructor utilizes 0 parameters to assign safe default values. The parameterized constructor explicitly accepts parameters, assigning immediate custom values. Finally, constructor overloading utilizes multiple distinct constructors for ultimate architectural flexibility. These strategies serve escalating roles in software design. Default mechanisms ensure baseline structural safety when starting data is absent.
Parameterized mechanisms deliver precision state control when that starting data is available, and overloading mechanisms ensure structural agility through compile-time polymorphism when that incoming data is highly variable. Mastering these three mechanics provides the technical foundation needed to manage how data enters an object and how that object is safely initialized in memory.